This video looks at right-hand rule 1 with a current carrying wire. So this is like part 2 of right-hand rule 1, and we're also going to look at loops. Now, with right-hand rule 1, we looked at, in the last lesson, Q's moving, right? Well, if we have lots and lots of charges moving, then we have current. Okay, so right-hand rule 1 continued deals with lots of moving charges or current. Now the same rules still hold. Right-hand rule for positive, and for negative you either flip it or you use your left hand. Now here's the equation if you have a current rather than a moving point charge. Looks a lot like F equals QVB sine theta. They look a lot alike. Current instead of charge, length, B is still there. So I is your current. Units are amperes. L is the length of the wire experiencing that magnetic field. B is the magnetic field in units of Tesla. And in this case, angle is your theta, and it's the angle between the magnetic field and the current. Let's look at an example. A 1.5 meter wire carrying 3 amps of current. So L equals 1.5 meters. I equals 3A. Experiences a force of 0.75 newtons in the positive x direction. Determine the direction of a magnetic force acting on an electron negative 1.6 times 10 to the negative 19th, that is moving at a velocity of 4.5 times 10 to the 6th in the negative x direction. Okay, so we're looking at for FB of a moving charge. Well, that equals QVB. So we need to find B. But we can do that using this up here. F equals ILB sine theta. So F equals 0.75, which equals 3 times 1.5 times B times sine theta, which is 1. So you get 0.75 divided by 3 divided by 1.5, or just divide it all by 4.5, and you get B equals 0.167 Tesla. Now the direction of B. The force, so your palm is in the positive x direction. The current is into the board, so it's into the page, while the force is in the positive x direction. So point your palm. Now you're looking at your current. We're assuming conventional current. So your palm points in the direction of the force. Your thumb, which represents current, is into the page. So your fingers point this way. And that's the direction of your magnetic field. Now for the second part, if we want the direction of the force, we know our magnetic field is this way, and our negative charge is going this way. Okay, so you have two options. You can use your left hand, or you can flip it when you're done. Okay, but you should get that your force is out of the page, represented by an O. Now to find the magnitude, that's the direction. Magnitude equals QVB sine theta, which is 1. So that equals negative 1.6 times 10 to the negative 19th times 4.5 times 10 to the 6th times 0.167. And I get 1.2 times 10 to the negative 13th. And that's your force in newtons out of the page. Alright, so what if instead of having just a straight wire, you have a loop, a wire loop? So you have a magnetic field going through this wire loop. And this wire has a current traveling through it. Now, the sides of the loop that are parallel experience no force because of the angle. The other sides make a little bit more sense when you look at them here. You have this magnetic field. Okay, in this one, the current is in an opposite direction of this. So your forces are in opposite directions. But it's a spinning loop. So if you create a pivot point, your forces aren't in opposite directions, but your forces are causing an overall torque. They're causing it to spin. So spinning means you have a torque. Now if we're going to solve for the value of that torque, we're going to take the force on one side of the wire and add it to the force on the other side of the wire, or the torque on one side and add it to the torque on the other. So we find our force on one side. We have a loop. This side is length A, this side is length B, and you have a pivot point in between. So you have this magnetic field. So you got B times your current, which is I, times A, which is the length. Now that's your force. You have to multiply it by R to get your torque. So torque of one side plus torque of the other. Now, we're going to simplify R down. R, rather than being, the radius, you say, okay, well this whole side is B, so R is B over 2. Okay, like that. So you plug it in, simplify it out, and you get A times B. A times B is the area of the loop. Right? A times B is the area of the loop. So you get IB area over 2 plus IB area over 2. And that adds up to be this. Alright, take a second, look over this again. Now just figure out how I got there. It really is very cool. And you end up with this equation for torque. Now, N is added into this equation. N is the number of loops. Basically, if you do it again and again and again and again, every loop, you add torque. You double it, or you add another one. So, if N equals 2, it would be twice as much, and 3 times as much. Now, electric motors. This is how electric motors work. You get this loop. Okay, and you have this current flowing through it. So an electric motor, you send a current through the loop, and there's this magnetic field. And you experience a torque, right? A torque causing it to go around. And the torque causing it to go around. And here it's perpendicular, so it's not really going, it's just going to keep going due to inertia. Now the problem occurs when you get to this point. This is what they had to solve with electric motors. The torque direction changes. The force directions do not, right? But the thing is still trying to spin in this direction. But now, the torque is causing it to try and spin that way. So how did they come up with solving that? Well, there are two ways you can solve it. One way is by introducing a direct current. So this is an example of a direct current motor. See how you have a current going through it and it causes the thing to spin. Now that black part on the spinning, that's basically a point where we say no current can go through here now. Okay, it cuts off the current. And it cuts off the current at the point where the torque changed. The direction of torque changed. So it kind of says, okay, we're just not going to have any force during that point. That's one way to solve it. The other way to solve it, which is the way that it happens in most of your appliances, is we use alternating current, which means the current direction switches. So where this was out of the page, it is now into the page. And by switching the direction of the current, you switch the direction of the forces, causing the torque to continue in the same direction. And this is how fans and blenders and power drills and things work. It has the loop going around in the same direction. Now, I personally have a favorite in electricity generators. I like AC electricity generators. Now, part of it is because of where I'm from. I'm from near Niagara Falls, and Niagara Falls was the first hydropower station, and hydropower, like most electricity generators, are AC. And what happens is, you have the spinning loop, and it looks a lot like the other one. But here's what happens. Before, we used current to spin the loop. Now we're spinning the loop to produce current, or to produce a potential difference, which is related to current. Okay, so you have this magnet, and you use the waterfall hydropower, or whatever the power plant uses, because, you know, a lot of them have turbines. Coal power plants use turbines too. They spin this in the magnetic field, and it causes this potential difference. But it causes it to alter, to, you know, go back and forth, which works really nicely because actually alternating current travels better than DC. It can travel for longer distances and it lasts better. Alright, let's try a problem. A circular wire loop of radius of 1 meter is in a magnetic field of 0.5 Tesla. And it's normal to the plane, so its theta is 90. Oh, sorry, normal to the plane makes an angle of 30 degrees with a magnetic field. The current in the loop is 20 amps. Now let's see. It's placed in a magnetic field. The normal of the plane of the loop makes an angle of 90, or sorry, angle of 30. So, if I go back and look at the picture, let me find a picture that I can use. Alright. Now I'm looking to see if my angle should be 30 or if it should be 60. Magnetic field, the normal makes an angle of 30. So something like this one right here. Right? Magnetic field, the normal makes an angle of 30. Okay, so theta should be 30. Sometimes they like to throw something at you where they kind of give you the wrong angle. They don't give you the angle between I and B. They give you the other angle, at which point you have to say, well, it's not 30, it's, 60 or something else. So you got to pay attention to that angle. Now it's a single loop, so n equals 1, b equals 0.5, I equals 2, area equals pi r squared, so that equals pi times 1 squared times sine of 30, which is 0.5. And I get t, or tau, equals 1.57 Newton meters.